We are discussing non-dimensionalization of equations, and in which we need to non-dimensionalize so that it is easier to work with the variables and it is easier to work with the real flow situations, trying to model them in at a laboratory scale. And for that, one of the necessary things is to normalize the equation. Normalizing the fluid equation of motion is so that the equation becomes dimensionless. We have already discussed discussed this thing, that the equation's dimensions should be the same. Each term occurring in an equation of motion should have the same dimensions on each side of the equation. If it is not so, there is an error somewhere. So they should be the same. But then we come to another step, that trying to normalize them. By normalizing them, it means that we will have a uniform dimension or no dimension at all, and just a number. And for that, we divide by certain variables each term of the equation by certain variables that are appropriate to the fluid flow as well as to the equation, and then we obtain the normal equation. If the non-dimensional terms in the equation are of order unity, the equation is called normalized. For example, if there is a term occurring with a radius r, for example, of a circle, and we divide by a radius of a sphere or certain number that is representing the radius, then dividing each term with the same number will render it equal to 1. So r by r will be 1. Similarly, if there is a velocity term and we divide velocity by velocity, it will be 1. But the velocity term with which we divide will be a typical representation of the fluid flow. It has to be taken from the fluid flow situation, not in an arbitrary manner, otherwise it may lose its relevance. But then it becomes equal to sort of 1, and it becomes non-dimensional and normalized. Each term in a normalized form is dimensionless. Of course, non-dimensional means that it is dimensionless. In the process of non-dimensionalization, an equation of motion, non-dimensional parameters often appear, most of which are named after a notable scientist or engineer, whoever first used that term, or first ever time that the person or the scientist or the researcher developed that number, used that number for his research work. And if that was found to be very useful in everyday fluid mechanics applications, fluid flow situations, and experimental and theoretical work, then that number, that parameter was named after the scientist. And there are many examples. One of the very common example in such cases is that of Reynolds and also the Froude number. So these two became very famous because they are very commonly used. The Reynolds number is a ratio of inertial forces and the viscous forces, whereas the Froude number or Froude number is a ratio of the inertial forces and the gravitational forces. This process is referred to by some authors as inspectional analysis. So, normalizing the equations is also known as inspectional analysis of fluid flow, and as well as by implication, the equations of motion.